here are the strange aspects of quantum physics, and that give rise to things like the laser printer and solar cells and your computers. Leon Letterman, a Nobel laureate, came up with a figure for this by looking at it seriously. He said he believes that 25% of the gross national product of the United States today is founded on quantum mechanics. And he's a smart guy who does his homework. I think he's probably right. When you look at the things that are made possible by quantum mechanics, by quantum mechanical behavior of objects. Now, the wave-particle stuff is something you're not even aware of. How do you notice this? Well, the most important, well, let me mention the other properties. Wave-particle means that every particle you see is really a wave packet. Now, there's a wave packet with just one nice frequency in it. This wave packet has a pretty clear energy. Whatever this frequency is, you multiply that by this constant we know about called Planck's constant, which you don't have to know the value. And that'll give you the energy of this thing. When this wave is absorbed, that's how much energy will be absorbed. You know, if this thing, let's say this is a wave of light. It's a particle of light. When it hits the surface, that much energy will be absorbed. If we have a wave that's twice the amplitude, but the same frequency, how much energy will be absorbed when this hits something? The answer is, in this case, it's going to be h nu, hf, which may be equal to, for example, 2 electron volts. That's the energy of visible light. So you shine a light on a surface, and the energy absorbed is 2 electron volts. What happens if I take a wave packet that has twice the amplitude, and it hits the surface? Well, I mean, maybe the whole thing bounces off. And there's no energy absorbed. That's possible. But there are 2 other possibilities. One is that 4 eV will be absorbed. After all, it's twice the energy. If it, you know, I mean, it has twice the amplitude. You think it has more energy, but wait a minute. I said it was equal to this. I'm confusing you. What's going on here? Here are the possibilities. No energy. That's if it bounces. 4 eV, all absorbed. But there's another possibility. 2 eV bounces, and 2 eV is absorbed. These are the 3 possibilities. What's going on here? Let me make it simple. When you have a wave with this frequency, there is what's called a quantum of energy. And this is the quantum of energy. It depends only on the frequency. If you have a bigger wave with a bigger amplitude, then we say this contains 2 quantums of energy. Except the plural of quantums, we use the Greek plural for it's called quanta, the plural. So this wave, when it's absorbed, you'll get either it bounces or you get 2 eV. This one, when it's absorbed, either it bounces or you get 4 eV, or half of it bounces and you get 2 eV absorbed. In other words, the energy in a particle wave is quantized. When you absorb it, you may absorb, if it's a big wave, you may absorb this much. This is called 1 quantum. You may absorb twice that. That's 2 quanta, 3 quanta, 4 quanta, but never in between. The energy you absorb from light is always some multiple of this fundamental number, which for visible light is 2 eV. So if you have a surface here and you let some light on it, the minimum amount you can absorb is 2. Not 1. You can't get 1. You can't get 0.5. It has to be 2. Or it could be 4. Or 6 or 8. It has to be some multiple of that quantum. We have a terminology for this. We say light comes in photons. See, that's what a photon is. A photon is that 1 quantum of light. We use this term as if it's a particle. But in fact, it's a particle wave. But when it's absorbed, when it changes, because it's being absorbed, the energy always comes out in some multiple of this basic unit. So it's behaving as if it were made up of individual particles. In fact, light is not a particle. Light is not a wave. It's a quantum wave. But it has this particle-like behavior when it's absorbed or when it bounces. So this is what gives us the illusion that light is a particle, because it has a particle-like behavior. This is true for all oscillators. I mean, just everything is this energy rule, the quantization of the energy, is one of the. This is what gives the physics of quantum physics its name, is the fact that it's quantized. It appears in many, many situations. I'm going to show you how it appears in the atom in just a moment. Now, another feature of quantum mechanics, which is more mysterious, is that when this wave can just go along just happy. But it's hard to measure, because if you measure it, the process of trying to measure that a wave is there makes big changes. For example, if you have a light wave going by and you're trying to measure, is there anything there? Oop, there's a quantum. But now the wave has changed. It has one less quanta of energy in it. Any measurement of any particle wave changes that particle wave. That means you may have found out what it was, but it's not there anymore. That's really strange. Do we understand this? No, this seems to be the fundamental rule. This is, I mean, whether you believe it was Mother Nature or God who created these rules, those are the rules that were created. Why were they created? Well, you've got to find your own way to get that answer. I don't know. Maybe because they wind up making life more interesting, as you'll see. But anyway, those are the rules. That's what happens. We can't understand those in terms of anything more fundamental, or we haven't been able to. You try to understand things more fundamental. What that usually means is that you are trying to understand this in terms of springs and levers and particles. That's what would make you happy and say, oh, now I understand what's going on there. You see this little spring and lever inside there, and that does this. But springs and levers don't exist. Everything is quantum waves, I mean particle waves. So you could ask, what could I explain it in terms of that would satisfy you? It doesn't seem to be anything. And so these are the fundamental laws. And why they exist, you have to make your individual prayers to God. Maybe he will tell you when you are in heaven. I don't know. But these are the rules. These are the laws. These laws, the quantum leap, is related to both the energy rule and the measurement rule. So we'll get to that in a moment. And the quantum leap is also related to the energy gap, which I'll now talk about. The energy gap, which gives rise to the quantum leap, is the key concept behind almost every one of these technologies. There's the laser, which is a quantum chain reaction based on the quantum gap. Didn't mention down here quantum computers. Probably won't get to that today, maybe next time. Which are in all the newspapers nearly once a week about quantum computers. Everybody thinking they're making a little bit of progress on how you might someday have a quantum computer that would work. But I'm willing to bet that not in the next 20 years will we have a useful quantum computer. Quantum computers are based on actually something I didn't quite state here, which is the principle of superposition, which is related to some of these things. But look, so these are the key principles. Let me now talk about the energy gap. Now, the importance of the energy gap, I can't exaggerate. It's just the key thing to everything here. This is an aspect that is intrinsically quantum mechanics. In ordinary physics, if you have a spring, you can make it, or a wave, you can have any amount of energy in that wave. In many situations in quantum physics, you can't. There are certain energies that are forbidden. These forbidden energies give rise to the energy gap. So let me talk about how these forbidden energies arise. It's related to the fact, this first thing here, you have a wave particle, and the energy is given by the frequency. Imagine an atom. Now, the Earth is going around the sun. And suppose it went a little bit slower. We'd have less energy. It would still go around the sun. It would just go in a slightly different orbit. You like to think from old classical mechanics that the orbit of the Earth around the sun could be anything. Likewise, for an electron around an atom. You think you have a proton in the hydrogen atom, and you have an electron going around. And you could give it more energy or less energy. You could have it go in different orbits. If it goes out here, it'll be going slower. So here it's a little bit faster. But gee, you think it could go in any orbit whatsoever. Well, that turns out not to be the case because of the fact that it's not a particle, but it's a wave particle. And in all these cases, the wave packet is longer. The wave packet, for all these interesting cases, this distance here is longer than the distance around. So what happens is the wave packet catches up to its own tail. Now imagine you have a wave, an electron wave going around, and it's really a long packet, and it catches up to its own tail. And suppose it gets right here, and I didn't have it really happen here, but let's say I could arrange it in just such a way that it cancels itself. Then what happens to the particle? Does it disappear? Can a particle is disappearing? So what happens? Suppose it doesn't quite cancel, but maybe on the third time around it'll cancel. It doesn't cancel on the first time, second time, but it's off by a little bit. And on the third time around it cancels. The particle will disappear? Can't have particles disappear. That's true. The particle can't just have the energy disappear. What happens is that a wave in an orbit where it would cancel itself just doesn't exist. You cannot get into that orbit. Because if you did, you would cancel yourself. This is the perverse part of quantum mechanics. If you violate the rules, you don't exist. In this class, if you violate the rules, you just get caught and punished for cheating. But it's more severe in atoms. If the wave cancels itself, you can't put that wave in there, because it will cancel itself when you try to put it in there. The interesting result is that not all orbits are allowed. And Niels Bohr worked out for the first time, this is 100 years ago, he worked out what orbits were allowed. And here it's going slower, right? Slower is a lower frequency, and it's a longer way around. So if you look at which orbits are allowed, it turns out there are only certain orbits that are allowed. There's maybe this orbit is allowed here, and this orbit, and this orbit. Actually, as you get further and further out, you find there are more and more and more and more orbits. These are called the excited states because they're further away from the nucleus. Because they're further away from the nucleus is pulling them in. As they fall in, they could gain energy. These things are less tightly bound, less bound. They're not as close to the nucleus, so they're not as tightly held on. These outermost orbits are the ones that provide electrons for metals to conduct electricity. They're so loosely bound that a slight extra force can pull them off the atom and bring them onto another atom. But the ones that are in close are the really tightly bound ones. Those are really moving very fast. There are a large number of these excited orbits. Eventually you get to the orbit that's so far away that it's like escape velocity. And those we call the unbound orbits, the electrons that actually aren't tied to an individual atom. So the picture of the atom now is you have a proton in the middle, much smaller than this, because you remember it's like the mosquito in the football field. It's really tiny. You have the electron that's going around. Now, I've drawn this electron as if it's moving on a line. In fact, the electron is spread out in three-dimensional space. And those of you who have studied chemistry have probably seen pictures of these things, where here's the electron, and the orbit might look like this, like two big bulbs. Okay? And what it really is a wave, a big wave. Here's a big wave with very low frequency, okay? It has two cycles, out, in, out, in, out in. That's 2 cycles. I could have an orbit that has many more cycles. Here's an orbit that has only 2 cycles. And this is the kind of bulge that you get that are drawn in these kind of diagrams, except the bulge, the electron isn't really confined to the plane of the blackboard. It fills out, so you get this kind of a space here. So this is what's going on with these orbits. And the interesting result is that the orbits that you get have to satisfy this rule. It's a very strict rule that the wave has to exactly come back to the same place. It's like a slinky going in a circle, and the wave can go just fine as long as it's not canceling itself. The wave just keeps on traveling around, but there are only certain orbits. Now, if you have something else in it, like 2 protons, that's called a helium nucleus. And then the orbits will be different. So every atom on the periodic table will have different orbits. You put 2 atoms together, and this proton affects the electrons in this other atom, and so you put 2 protons together, and the orbits are still different. For some of these things, we could actually calculate what they are. It's much easier now using computers than it used to be. For many of them, they're just too complicated. You know, when you have 92 electrons in uranium, it's really hard to calculate. You can't do that on the back of an envelope. We can't even do that in our best computers. But the calculations can be done for the light elements that have very simple nuclei. So, where are we? We have shown that when you're in an atom, only certain energy electrons are allowed. That's the key to most of these devices. Now let's talk about the thing I showed you last time. You take a mercury lamp. Some people came up to wonder, where is the mercury lamp? It's gold covered with black, except for a slit on the front, where the light came out and was spread out here over the screen, and we saw those lines. Okay? If you have an atom, and there are several possible orbits, and this is the one the electron happens to be in. Now, could it change its orbit from this to this orbit? It can only change to allowed orbits. It can't exist in other places. To do that, it would have to change energy. In fact, it's being pulled in by the attraction. And so it's going to be, it's picking up velocity, but this is actually doing work on it. It has to lose energy to get in closer. To lose energy, it has to emit that energy. The way it does this in an atom, when you're jumping from one level to another, you have to lose energy. You could do it through heat. So if this atom bounces into another atom, then this one can drop down, and this atom will pick up some speed. That's one way it happens. But you have to have some place to put the energy. Typically, if you have a high gas with a lot of pressure or a solid or something like that, the electron can jump down to this lower energy level. It's actually a higher velocity but lower energy. A little bit confusing, but that's because it's closer to the nucleus. It's like the spring is, the spring was stretched, and you're losing some energy as it's pulled back in. It has to lose energy to go to a lower energy level. To do that, it can do it by colliding with another atom, but suppose it's a gas, and there's nothing around to collide. It can still do it, but it has to emit that energy. Now, you have an electron whose velocity is suddenly changing. When that velocity changes, it's like shaking the electron. You can emit an electromagnetic wave, and you get light out. So typically for a gas, where you don't have the collisions, when the electron changes its energy level, you emit light out. The light has exactly the energy. That's the difference between this orbit and this orbit. That's where the energy goes. Since these orbits are quantized, that means the light that comes out has to be this value or this value. In this case, there are only 2 values allowed, but there may be other orbits. The light can have only certain energies. Those energies then tell you what frequency it has by this. In other words, light coming out of an atom in a gas will have only certain frequencies, and that's what we saw in the demo. We had a mercury gas. We heated it up. From collision, some of those electrons went into outer orbits. When they fell back down into a lower orbit, they emitted the light, that light came out with frequencies that were equal to the difference in energy levels. This is why, since mercury will have a different energy levels than hydrogen, than helium, and so on, we will see, if you look at a gas, you can tell what's in it if it's hot by looking at what frequencies are emitted. Very important if you suspect, for example, that some factory is using some chemical that is controlled, that they're not allowed to emit into the atmosphere. You look at their smokestack. If it's hot gas, you look at the light that's coming out. Light that's coming out will have these colors that tell you what's in it. This is a kind of remote sensing that's based on the spectrum, which comes about from quantum mechanics. Now, suppose the gas is cold. Then you can do something else, which is to send light at it. You shine light on the gas. If there's an electron here, this electron can absorb energy. And when it absorbs energy, it has to absorb only, it can't absorb any amount. It can't go into this orbit or this orbit. It has to absorb that much energy. So by shining a bright light at a substance and seeing what energies it absorbs, you're also measuring what it is. You're identifying. This is a very, you'll see flame spectroscopy in chemistry, where you take a little substance and you put it in a flame. That's really to turn it into a gas. The heat puts some of the electrons up in the excited levels. As they leave the flame, they cool off. The electron drops down, and the photons come out with a frequency that tells you what the energy differences are. You can get a catalog of every atom. You don't care what the energy levels are. You're more interested in the energy differences. Sometimes you'll have a jump that goes from here to here. The electron will jump that much, and you'll get a more energetic photon coming out. So let me summarize what I just told you. This is the sort of thing you would want to be able to say in an essay question, for example. That when you are identifying a gas atom by using some law of quantum mechanics, good question, how does that work? Why does it work? Well, it works because the energy levels, only certain energy levels are allowed. The reason they're allowed is because these things are really wave particles, and only orbits where the wave particles don't cancel each other are allowed orbits. There aren't very many of those. Every atom has a different set. If the gas is hot, then in a collision, sometimes the electrons will pick up energy and go into an upper level. After a while, they will lose energy by emitting a photon, but the energy they emit is always one of those energy differences. And by looking at that, by looking at the frequency that comes out, you can tell what that is. That's mercury. Yeah, not only that, not only is there one line, but I see this line and this line. That's two lines. And in the mercury thing we saw yesterday, there were about 5 lines that we could see relatively easily. That combination of 5 lines is like a fingerprint. That shouts out, mercury. If it's your job, that would shout out mercury. I mean, I'm not going to ask you to memorize the mercury spectrum. I don't know it either. But if your job is to detect polluters, we're not allowed to put mercury in their smokestacks, and you measure the light coming out, and you see that pattern of 5 things, then you got it. We see those patterns coming from the stars. That's the only way we know what the stars are made out of. It's because the light comes out. And the most interesting light comes from the atmosphere of the star, where it's a gas, not the heavy stuff where it's really dense. Because there, you don't tend to get the lines, because the electrons can lose their energy from collisions. They can give up their energy in that way. But once you get out into the gas, the only way they can lose energy is by emitting light. That light comes out in definite lines. You look at that, and you can tell what the stars are made out of. So we know the stars are typically 90% hydrogen and 10% helium, with little trace amounts of things like carbon and iron. You could see those. You see the lines of carbon and iron. You see them in the sun. You see them in the stars. We look at the different stars. We could see what the stars are made out of. We can look at the sun. We look at some stars, and all you see is hydrogen and helium, nothing else. These are the kind of stars that are not very bright, and they have probably been burning for 10 billion years. Because you could see that they're massive, but they're not very bright. Those stars tend to be hydrogen and helium and nothing else. The older stars like the sun, they're not an older star, but the stars like the sun have carbon in them. But not the really old stars. The sun is a relatively young star. We can measure its age to be 4.5 billion years. We'll talk about that in a couple weeks. The universe is 14 billion years old. The sun, we believe, is a secondary star. based in part on the fact that it has these interesting things in it, like carbon and iron. Without carbon and iron, life would not be very interesting. But we can tell because, we're made out of carbon. We have hydrogen, yeah, but we have carbon. We need nitrogen, a couple things like that in order to make interesting molecules so that, we can live and teach physics and learn physics. We have to be pretty complex organisms to be able to sit in on a class like this and actually learn physics. And that requires these other elements. And we know now there are these stars that don't have them. And those stars, very unlikely to be any life in systems that consist only of hydrogen and helium. You can't make any interesting compounds out of hydrogen and helium. Without interesting compounds, how do you make life? Well, if you're a science fiction writer, you can come up with something, but odds are it's not going to work. But if you have carbon, then there's some chance. Carbon makes the most interesting molecules of any atom. So this is spectral identification. But this energy gap is the key thing. Now, in other geometries, the most interesting geometry, well, let me talk about a few things here. Okay, let me talk about the laser printer. And also the Xerox machine. So I put that there because we're being webcast. See, I don't want to get into legal trouble. By the way, I'm curious. Let me just take a quick survey because I haven't done this. I've been meaning to do this. And I have no idea what the answer is. But I would be interested in knowing how many of you have actually listened to one or more podcasts. Raise your hand if you listen to one or more podcasts. So let me just get a survey. I get about a dozen people, maybe 20. Interesting. We have people. I get email from people in Norfolk, Virginia, and they're saying, "Oh, please keep on podcasting. I listen to your lectures every morning when I jog." Okay, so I was just curious how these things are going. They're going to do something new in the podcast, and keep on developing this technology. Not that expensive to do, apparently, so it's a good thing. Okay. By the way, those of you out there, listening to this from Walla Walla or Timbuktu, send me an email, ramuller@lbl.gov, and let me know that you're listening to these podcasts. I find it amusing. Okay. Now, E equals h nu. I mentioned briefly that when an electron, or rather when a wave of visible light hits an atom, it can excite that electron to a higher level if it's just the right frequency. That's called really an absorption line. Oops, nothing back there. Try this one. Suppose you have a metal surface. Now, in a metal surface, you have atoms where the outermost electron is so weakly bound that it can easily jump from atom to atom. It's so far away from the nucleus, there's not much of a force holding it on. Okay? If it gets far away, and it doesn't take that much energy to knock it out. If you have a surface consisting of metal, although this will happen actually with just about any surface, and you hit it with a photon, and the photon has enough energy to take that electron and just knock it up one level, then what will happen is the thing may fluoresce. Remember what fluorescence is? The fluorescent tubes in our lights. If you have a fluorescent tube, it's covered with a white paint. The electrons travel in the fluorescent tube, and these electrons take the atoms in that fluorescent tube, and they bang into it, and they typically take that electron. They not only give the whole atom some energy, but they will take that electron and put it up into an excited level. This happens in the mercury inside these fluorescent tubes. Now you have a gas with an excited electron. It could lose its energy through a collision, but that's not very likely in this gas because there aren't that many other atoms around. It's much more likely to lose its energy by jumping down to another level and emitting a photon. And that's what happens inside the gas of a fluorescent tube. So you have the electrons passing through the tube. They excite the atoms. That's the term we like to use, excite the atoms. Again, stealing a word. Giving them energy. We're giving them energy by taking the electron and putting it up into a higher energy level. Okay? That electron will then, at some point, lose its energy again, not through a collision because it's only a gas, but instead will lose its energy by emitting a photon. The energy of the photon it emits for mercury gas, the key photon, the one we're most interested in, is the ultraviolet photon. And mercury is chosen because it emits this really nice ultraviolet, energetic ultraviolet photon very efficiently. A lot of the energy goes into this ultraviolet photon. It's a single line. We actually saw that line here last time. It's one of the invisible lines. Now, with nothing else, if you didn't put this paint on the surface, you would have a tube that emits this ultraviolet photon. It turns out that this ultraviolet photon is a really good frequency for destroying DNA. It's a bad frequency. You don't want to expose your skin to this stuff. Okay? Really, so it's good at destroying DNA, which is why we use tubes like this to disinfect materials, surfaces, tools. In an operating room, the doctor will scrub and scrub well, the doctor doesn't do the scrubbing mostly. He scrubs his hands. He has his assistant or her assistant scrub all the tools, and they put it down under a light like this that doesn't have the surface. And the ultraviolet light comes very good at destroying the DNA of bacteria and even viruses. Viruses are often RNA or DNA. This gets in there. It just happens to be just the right frequency to mess these things up. So it's very good as a disinfectant. We're not using it as a disinfectant here. Instead, what we do is you put a surface on here with a phosphor. What a phosphor does is this. It has an atom in it with certain allowed orbits. The phosphor, the ultraviolet, when it hits this electron, will knock it up all the way up to this level. They pick a phosphor where this is pretty efficient. So the ultraviolet light is absorbed in the phosphor, and the electrons are now in an excited level. So this is the ultraviolet energy. It's a big gap. Big gap means high frequency, means ultraviolet. Now what happens is the electron's in this orbit. It's a gas. Well, it's not a gas. It's a solid, but it's a special kind of solid where it's not likely to lose its energy through collisions. And it loses its energy, but it does it in two steps. Now, this is really important because the fact that it does it in a small energy step means the frequency is lower, right? E equals a constant times the frequency. A small energy gap means a smaller frequency. Smaller than ultraviolet is visible. So this thing jumps up, absorbs the ultraviolet, and then emits two visible photons. You've converted the ultraviolet light. One photon of ultraviolet light you've converted to two visible photons. And so we get this light coming out of the ultraviolet light because the ultraviolet light is absorbed. First, this is a quantum mechanical thing. It jumps down, emits this ultraviolet light, which happens to destroy DNA. But if you have an uncovered tube, it's really good for destroying DNA or for Halloween purposes because it's a good source of ultraviolet light. And then you can stand around and have your white shirt glow in the dark. Or you can put the phosphor on there. And then the ultraviolet light is absorbed by the atoms, which then emit a lower frequency light by basically going through two jumps where there was just one excitation. And that's what gives us our light. It's also what gives us our light in our computer screens, which have little phosphorescent tubes in them. Computer screens are really quite interesting. If you have a laptop, these flat computer screens, a lot of people don't know how they work, because you never take them apart and they can't be repaired. But if you're looking at it from the side, here you're looking at the screen, and here's this light coming out from your screen, it's actually coming from one or two, or in some desktop models, 4 fluorescent bulbs that are hidden at the top and the bottom. These fluorescent bulbs emit light down here, up and down and up and down, so you have this light going back and forth and back and forth. The inside is really, really bright. Then what they do is they put little things in here that scatter the light. So the light, some of the light scatters out. And that's what gives you your bright screen. But they're actually fluorescent tubes at the top and the bottom. Next time you have a broken laptop, rather than just dumping it in the trash, take it apart. And you'll be amazed at these tubes. They're such fine tubes, just a few millimeters in diameter. Fluorescent tubes just like this. They're now the main source of lighting for flat displays. Now, another way, okay, let's consider this is the case now where the ultraviolet light excites this and then drops down. Suppose you pick a special material. The best one historically turned out to be selenium. Okay, there's selenium. Famous in a certain technology because the Xerox Corporation patented it. Patents in those days lasted 17 years, so the patent for selenium finally ran out, and then everybody started making Xerox machines. Xerox machines makes use of the fact that in selenium, you send in visible light, and the electron in the selenium atom gets so excited it pops back out. It shoots right out. This is called the photoelectric effect. Photoelectric. Photoelectric effect. And it's just the fact that visible light hitting a selenium surface will cause it to lose an electron. The energy of the electron is equal to the energy of the photon. It loses a little bit coming out of the metal surface. So you don't get all the energy in the electron, but you get a good fraction of it. So shining light on a surface knocks electrons out. That's the photoelectric effect. That's the key to many of the technologies we're about to talk about. That's important for solar cells. That's important for digital cameras. Light knocking out an electron out of the atom. It does it because the photon of light has enough energy that when it's absorbed, the electron can't just go into a slightly different orbit. It has to absorb all of that energy. When it does it, it absorbs enough. It's like giving it escape velocity from the atom. That's called the photoelectric effect. The way a Xerox machine works is it uses the photoelectric effect. Let me go over here. And by the way, laser printer works almost the same way. In this old-fashioned Xerox machine, laser scanners work the same way too. What you do is you have a sheet of selenium. The sheet of selenium is usually not flat. It's typically on a drum. Okay. But it could be flat. So here's the surface layer of selenium on this surface. Now what you do is you make this work like a camera. You basically have the object, you have a lens, and you project that onto the drum. Now, typically you do it one line at a time. So what they'll do is you have the object, and they'll have a light sweep down and really illuminate one line of the object at a time. That one line will be projected on this part of the drum. There may be the foot. If you're photographing a person, the person's foot will be on that. And then the light will move and illuminate a different part of the object, and that will illuminate a different part of the drum. You could have done it with just a single lens, and in the old days they did that. But basically what you're doing is you're putting an image up here of whatever it is you're photographing, usually some text. The light knocks electrons off wherever it's bright. The brighter the light, the more photons are coming in, the more electrons are knocked off. The electrons are knocked off, you're left behind with something that's charged. And the charge, the distribution of charge, if you look at the surface of the selenium, you know, if I want, you know, where are the positive charges where the electrons got knocked out? You know, they may be in this region here. Right, there's my famous face. And none over here. So wherever the image was bright, the electrons were knocked out. Okay. Now what they do is they put a smoke over this thing, and the smoke will be attracted to wherever the electrons were knocked out. And you wind up getting an image, because the charged particles will attract these smoke-like particles. Now you have an image on this roller. And you press the roller against the paper, and the paper will then take on that smoke, and you get a smoky sheet of paper. That's how a Xerox machine works. If you get that paper out, if your Xerox machine ever breaks down, and you go inside to get the paper out, you see this paper with a nice image on it. You say, oh, look at that. And then you discover your fingers are all smudgy, because that smoke is just lying on the surface. So there's one more step where they have to heat up the surface. To fix they have a glue mixed in with it. When you heat it up, it melts and becomes a permanent part of the paper. But that's basically how a Xerox machine works. A laser printer works exactly the same way, except it doesn't use a lens. What a laser does is it takes the signal, maybe a digital signal, like a TV signal, where you know how bright it is at every location. And what the laser printer does is it sweeps a laser beam across here with bright and dark patterns, exactly mimicking exactly what you need in order to get the pattern to make a image. Usually, the original Xerox machines were all only black and white, bright versus dark. Getting gray level was really a struggle. You have to do tricks just to make sure you don't get a negative coming out. You want a positive. With a laser printer, that's really easy. With a laser printer, you can just modulate the light to give whatever brightness or darkness you want. But this is the basic idea. It's using the photoelectric effect. It uses the fact that when light hits selenium or other metals that have since been patented, that electron gets knocked out. Now you have an image that's charged. It's not in ink yet. It's just electric charge. But electric charge will attract little pieces of ink. And so it becomes first the image is first in the light, then it's in the charge, then it is in the ink, and then the ink is fixed, and you got your Xerox image. Laser printer is basically a Xerox machine, trademark. They call them photocopiers these days because Xerox is so defending this name. They don't want to become a generic term like Band-Aids or Scotch tape. Band-Aids or Scotch tape people will get after me because they're still defending their names too. So they don't want you to use the word Xerox. It's like when you're in an airplane and you say, yeah, I'd like a Coke. Is Pepsi okay? You know, they're not allowed to give you a Pepsi if you ask for a Coke. Because Coke is not a generic term. It is a trademark name. So likewise, Xerox is a trademark name. These things are called photocopiers. That's not trademarked. And everybody here probably uses them. A laser printer is simply a photocopy machine using a laser. Now, why do you use a laser? One other question is, if what they're really using is a drum with selenium and quantum mechanics and charge, why do they call it a laser printer? A laser is part of it, but is that the real key thing? I think the history of this is really quite simple. The reason they call it a laser printer is that when they first came out, laser anything was the hot thing to be. Back in the 30s and 40s, you know what the key word was? Radio. You ever see old movies? And here you're watching this movie, and it says at the beginning, RKO, radio picture. They say it's a radio picture, right? And they have a tower. Beep, 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 beep. These old movies right at the beginning. And it's a radio picture. What does it have to do with the radio? Absolutely nothing. Radios were the high-tech of the day. Now lasers are the high-tech. So they call them laser printers, inkjet printers. Most of us use inkjet printers for almost everything instead of laser because they do colors better. For colors on something like this, what you have to do is break the light up into 3 different colors and then print 3 different images. Red, green, and blue, or cyan, magenta, and yellow. 3 colors so that your eye can be sensitive to in little dots. And that means 3 mechanisms to do it. Inkjet printers are sort of easier because their mechanism is just a little spray device that puts a little droplet down on the paper, and you could have your 3 cartridges in there, and they put the dots down, and it's not that much more complicated than having 1 cartridge in there. But for laser printers, it's hard. So most color printing these days is done with inkjet printers, and inkjet printers, as near as I can tell, do not use quantum physics in any significant way. But the same principle is what makes the solar cell work and what makes the, your digital camera work. So let me talk about that. Okay. In the solar cell, it's a solid. Now, analysis of a solid is a fascinating thing, and even the physics majors don't study this very much unless they take a special course in what's called solid-state physics. The interesting thing about a solid is instead of having 1 atom where things move around in circles like they do in a gas, in a solid you have a regular array of atoms. It's a crystal, and they're all laid out in a very regular array. And when they're in a regular array, you wind up getting phenomena that's very similar. What happens is when you have an atom, a regular array of atoms, instead of going in a circle, the wave, when it's going through here, bounces off these atoms. It bounces off and comes back. And then it bounces again and goes in the same direction. And there's so many atoms there that this bouncing is very, very common. Now, if with common bouncing, it better be that the wave that's going forward does not cancel out the original wave. So this cancellation phenomenon gives rise to a similar situation to what we have in the atom, in individual atoms. The math of this is very interesting. The basic physics is this bouncing that I told you about. What you wind up getting when you do these calculations is that you find, instead of there being many, many individual energies, there are bands of energies. Sometimes we draw these energies on a vertical scale, and you say the allowed energies, I'll put a dot everywhere there's an allowed energy. Those are allowed. These are allowed. These are allowed. This is the way it works out when you take into account this bouncing. Okay? I could go on for 20 minutes. Sometimes I do this for the physics majors and spend a whole lecture trying to make this plausible. It's not as evident as it is in the atom. So I'd ask you to just take my word for it that these are allowed energy levels. An energy level is frequently called a line. You saw that for the demo. The reason is we let the light go through a slit. And so when you look at it in the spectrum, instead of seeing one spot, you see a line. So they were called lines. For solids, the lines tend to be close together. So they were called bands. If you look at a solid and look at the spectrum, you find this wide area with many, 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 many lines. In the beginning, they didn't even see there were individual lines in there. They become bands. So these were called the bands because they were spread out in the spectrogram to look like wide areas. But the most fascinating aspect of this turns out not to be the bands, but the band gaps. You go into a solid, and you are an electron, and you could have this much energy or this much energy or this much energy, but not in between. These band gaps are the keys to semiconductors, to integrated circuits, to your laptop computers, to superconductors. The presence of these gaps are the key to almost everything. You have areas where the electron can't have that much energy. In superconductors, what this leads to is that an electron, when it's traveling with other electrons, and you're moving with all these other electrons, and you happen to bang into something, you pick up a little bit of energy from that banging. except if that little bit of energy throws you into a gap, you can't pick it up. Therefore, you don't. That's quantum mechanics. Let's say that again. For those of you, I want everybody here to concentrate on this. It's hard to say this in writing in the book. But in a superconductor, the electrons are all moving together in the superconductor. Okay? They are moving in an allowed energy level called the ground state. There's a gap right above them. If you hit them really hard, they can pick up energy and jump up to that excited state. But if they just happen to collide with something, they're not moving fast enough to pick up much energy. And if they did collide and pick up that energy, they would be in the gap. And that's not allowed. So the amazing result is, therefore, they don't collide. Therefore, they keep on traveling without colliding. That's what superconductivity is. Superconductivity is based on the fact that these electrons all moving together in what's called the ground state cannot lose any small amount of energy. And so the normal resistance that you get by small collisions is impossible, because then you would have to be in this gap. You'd have to have an energy that's not allowed. The fact that this would happen at all was not theoretically predicted. It was discovered in 1911 by Omnis. Real surprise. I mean, it's like X-rays. God, imagine what it must have been like around the 1900s. You think we're in a revolution today, but they had, you know, they were just discovering quantum mechanics, superconductivity, airplanes, automobiles. Quite an era. But in 1911, Omnis discovered that when you took certain metals and took them down to very low temperatures, they became superconducting. All of the electricity lost its resistance. Electrons could travel forever and not lose their resistance. People have done this for years. They make a little ring of electrons moving around in a superconductor, and they look at the magnetic field, and they say, does the magnetic field go away because this thing is losing energy? And it's not. Done this for decades now. So it's truly amazing. It's quantum mechanics. It's based on the fact that there's this energy gap, that the electrons moving together cannot collide, because to do so they'd have to change their energy into a forbidden region. So the energy gap is the key to superconductors, but it's also the key to such things as solar cells and your cameras, your basically digital cameras. So let me talk about that. How are we doing here? Remember here, in the photoelectric effect used in the Xerox machine, the light comes in and knocks an electron out. In the solid materials, in these crystals, the key is not to knock the electron out, but just to excite it up to a different band. The light knocks it up to another band. Now, the reason this is so powerful is not at all obvious. But what they do is they pick materials where this band is basically completely full of electrons. There's no room in it at all. No room. They knock it up into a band that has only a few or no electrons. That has the following amazing effect. Let's imagine this room were filled with people. And I said, okay, I want everybody to move over one seat. It would be pandemonium. It would be very hard to do. You'd be sitting there waiting for the person next to you to move, and the person next to you would be waiting for you to move. It really doesn't work very well. That's what we call, basically, filled states. And if you have electrons filling every state, you find it becomes an insulator. There's no place for an electron to jump to, and so the move doesn't take. If you have everything coordinated so everybody jumps together, you can do it. But if basically you're waiting for your partner to move, it's a very slow process. That's called an insulator. A classroom like this with empty seats works much better. If I ask, don't do it. If I ask each one of you to move over, a lot of you would just move over. Some of you, they're in little bunches there, and it would be a little bit harder, but they're not such big bunches. And of course, in a real solid, you wouldn't be bunched quite so much. Atoms don't make friends in the same way, and so if it's partly empty, then the electrons can move easily. in semiconductors, it's called a semiconductor. You have this band. It's sometimes called the valence band. You don't have to know that word. It's a technical word. They think of it as the insulation band. Remember, what a band is just energy. Now, this isn't a picture of things, how they exist in space. I'm just saying what energies are allowed. These energies are allowed. This is often called the conduction band. So here's what I want you to know. One of the key elements in semiconductors is the existence of these bands. If you shine light on a semiconductor, and there are other things you can do too, we're coming to that. That's the key to understanding computers. If you shine light on it, you can knock an electron up into the conduction band. When it's in the conduction band, think of it in the following way. I got this from a rather nice textbook that I was looking at last night. What is it? Bloomfield. Bloomfield wrote a nice description of this in his textbook, and I think it's really great. You have an auditorium that's full of students, and there's a balcony with very few people in it. I say, move over a seat. And you're kind of waiting for your neighbor to go, so not much happens. Okay? But according to Bloomfield's example, you knock a few of the students up into the balcony. You know, have a gorilla come there and go, whoa, throw them up. And I say, move over a seat. And all the gorillas start moving. You can actually get a lot of motion up there by just you get current flowing. This is what happens in a solar cell. This is what happens in a digital camera. What happens is you don't have electrons flowing up there, but what you do is when you shine light on them, they're knocked up into the conduction band. Once they're in the conduction band, current can flow. In fact, they'll accumulate up here, repel each other, and if it's a solar cell, what you're doing is taking these electrons up into the conduction band where they then create an electric charge that flows, and you get the energy out. In a camera, all you're doing is letting the electrons go up into the conduction band so you can detect that they're there because the current will flow. The number of electrons up there depends on the amount of light that's hitting the crystal. So typically, people use crystals. Often, the key crystal they use, the one that has proven most valuable, largely because it's inexpensive and easily manipulated, is to use a crystal called silicon. Whoops. So silicon, right there, there are others too, the ones below it. Germanium, very important. These other things near it, gallium and arsenic, these elements right here prove to be really important, partly because it's so easy to manipulate them by putting selenium is close by too, you'll notice. But the silicon is the key element. They put impurities into it because they do a lot of little tricks. We'll talk about some of those tricks that they do. But they put impurities in to make sure there are some electrons up there. And then they can put materials together to make junctions and diodes and things. We'll talk more about that. But right now, I want you to know that silicon is the most important crystal being used. Germanium is also important. The more expensive ones, some of the really tricky things, need germanium. The more expensive solar cells tend to be germanium. But silicon is cheap. And it gives rise now to a geographic location that you will find on some maps called Silicon Valley. And it's called Silicon Valley because they have made their fortune and a considerable fraction of the nation's GNP based largely on exploiting the crystal properties of silicon to make semiconductors, which are used not only for solar cells, but also for integrated circuits, computers, things like that we'll talk more about on Tuesday.